Please take it away.
Okay, thank you, Dennis, for the introduction. So I'll be talking about our theoretical proposal on quantum computing and also quantum information transmission using those mobile domain world textures on magnetic racetracks. So my talk will be based on these 3 papers. So if you get intrigued, feel free to check them out. First I would like to thank my collaborators, of course, our team from Basel, my current PI, Daniel Noss, and Warsaw Elena, and Stefano Bosco, who was a postdoc in our group, and last year moved to Delft as a young PI. And also our experimental friends from Germany, Stuart and Warsaw Banabi. And also friends from Japan, Tomoki and Guanxiong, who helped us with magnetic simulations. Okay, so my talk will be divided into 2 parts. So the first part, I will show you how to use domain wall as a conventional qubit for quantum computing. So in the second part, I will show you how to use domain wall as a flying qubit to communicate distant points on a solid state platform. Okay, so let's start with the background. Probably with this audience, I don't need to mention it, but anyway, let me do it quickly. So as I sketched here, imagine we have a magnetic nanowire, and on the one end, we have all the spins pointing upwards. On the other end, we have a domain pointing downwards. Then all the spins in between would smoothly connect these 2 domains, and this kind of profile is what we call the domain wall texture. Of course, we know that there are a lot of interesting ideas, interesting proposals based on domain wall textures, generally speaking, topological textures. One well-known example is the so-called racetrack memory, where we basically use the domain wall textures as a classical bit to process the information. And after that, of course, a lot of experimental activities are going on in this direction. And now in the lab, people can really control and manipulate the domain wall motion very nicely. For example, by magnetic fields, electrical current, or spin current, whatever you want. And even more impressively, they can drive the domain wall motion with a rather large speed, even over 1,000 meters per second. So all the stuff here I described, they are already achieved in the experiments. And for us, as a theorist, we want to ask, can we go beyond this nice picture? Well, a natural way for us to go is to push all this setup into the quantum regime and ask the question that, can we use this domain wall textures not only as a classical bit, but also a mobile quantum bit? So that's kind of the motivation. Well, the general idea is that this kind of textures, now we can make nanoscale. And if we cool down the temperature to, let's say, millikelvin, they should exhibit some quantum phenomenon. The question is, how can we harness this kind of quantum coherence in the problem, in the system? To this end, of course, we need to answer many questions. For example, how we encode the information, how we operate them, and what are the advantages compared to the existing platforms. We should provide some argument at least, right? At least in theory. Of course, there are always a lot of interest in the community in the quantum properties of topological solitons. Marcus already gave a very nice lecture on the first day, the first talk, on this quantum properties of skyrmion. Of course, our organizers, they also have many nice papers on this. So maybe if you want, you can also join us and explore this direction, provide your perspective, and yeah. Okay, anyway, before I dig into all the technical details, I just like to give you a very brief idea about the proposal. So whenever we want to use something as a qubit, of course, the first question we should really ask ourselves, is where we want to store it, right? So here we propose to use the chirality to do that. As I sketched here, it's very clear that we can rotate the spin from down to up in different ways. One way is what I sketched here, rotate the down spin from down to up counterclockwise. If you map all the spins onto this order parameter space, it would correspond to this red trajectory. And of course, you can also choose to rotate the spin also from down to up, but now clockwise. And then if you do the map in the spin space, you will see this blue trajectory. The idea is to use this chirality degrees freedom as a pseudo spin to store the information. For example, you can call this a positive chiral state as a spin up state, and this negative chiral state as a spin down state. Okay, so it's just a very brief reminder about this well-known DiVincenzo criteria. I think Dennis also flashed this, but anyway, the first 5 points, they're requirements for quantum computing, and the last 2 points, they are requirements, for quantum communication. So hopefully, I can convince you that the topological textures we have, generally speaking, they are not only good for quantum computing purpose, but also good for communication in the solid-state platform because of the mobility of this kind of textures. Okay, so of course, I need to tell you what ingredients we need to make this kind of textures qubits. The first thing we need is a stable domain wall. To have a stable domain wall is very easy. We just need to introduce some length scales in the Hamiltonian. Basically, for example, we can add an anisotropy, let's say in the z-axis. Then if we have this down-up boundary condition, naturally the solution would give us a domain wall profile. And here I wrote it down. I'm pretty sure you learned this in your classical mechanics class already. And the size of this domain wall is simply determined by the computation of these two terms, which typically on the order of several nanometers. Importantly, for this system, there are two zero modes. One is the capital X, which physically stands for the position of this domain wall. That's because the translational symmetry in space of this Hamiltonian, simply because this symmetry. And another zero mode, which is the azimuth angle phi. This is also zero mode because of this U1 symmetry in the spin space around the z-axis is clear. So if you set, for example, phi to 0 and plot this profile, you would get this positive chiral state. And if you set phi to pi and then plot this vector field in 1D, then you would get this negative chiral state. Because of this symmetry, in this case, it doesn't matter which phi you choose. It can be any value from 0 to 2 pi. If it's a pi over 2, then it's a block domain wall. It would rotate out of plane from down to up. Anyway, that's with these two simple ingredients, we would have a stable domain wall. And of course, we need to add more ingredients. So as I just said, if we have only these two terms, if we plot the energy of the domain wall as a function of the azimuth angle phi, it would be a flat line because the U1 symmetry. Then we add this easy plane anisotropy. Because of this term, as physically all the spins, they would like to stay within the xz plane. Then this phi, positive chiral state and the negative chiral state, they would be preferred. If you look at the mass, you will find that in this case, the potential for this domain wall would be a sine or cosine function, and one value corresponding to this positive chiral state, another value corresponding to this negative chiral state. Well, still, we have a high energy barrier between these two chiral states. In reality, it would be difficult for them to form a superposition or for them to tunnel to each other. Then we somehow need to bring this barrier down to this end. Let's look at the spin at the center here, and and also the spin at the center of this this negative chiral state. So one is pointing to the right, another one is pointing to the left. They are far away each other. That's why it's difficult for them to tunnel. One easy way to solve this is to apply a magnetic field in the y direction. So they tilt out of plane and get closer and easier to tunnel to each other. So that's the physical picture, but again, you can also stay down and write down the equation. You will find that indeed you would get a suppressed tunneling barrier.
Excuse me, so if you say you write down the equation, so this is not quantum yet?
Not quantum. I'm just describing the picture, you know. That's something you do before you do the calculation, right? Anyway. Sometimes you also want the detuning. Then that's very simple. You just add a magnetic field in the x direction. Just by looking at the picture, it's clear that if you apply a field in the positive x direction, then this positive chiral state would be preferred. Then this would create the energy difference or the detuning between these two values. Again, this is a sketch of the idea. Then once we have this idea, we sit down and do the calculations more rigorously. Here I just sketch some essential steps. Of course, the starting point is always the full dynamics of this system. Then we project onto these two low energy modes that I just mentioned. One is the space, another one is this azimuthal angle phi. And we will use this azimuthal angle phi to define the qubits and use the spatial coordinate to operate the qubits. And this spatial coordinate x and phi, they are coupled because of, we have naturally spin Barry phase effect in magnetic system. Everyone knows as a child, if you have a spinning top, you push it, it starts to process. So this kind of real space dynamics is coupled to the spin space. That's kind of captured by this coupling term. And then we project this azimuthal angle phi onto this low energy manifold, this chironic states. Then we would arrive at this simple Hamiltonian. You can see this tau operator here. They are basically Pauli matrices in this chironity space. And importantly, I want to point out that you see that you have this cross term, the coupling between the real space and this the spin space or the chironity space. This is an effective spin-opt coupling due to this spin Barry phase effect.
In reality, what does it do to the domain walls? Make them move in opposite directions. So opposite chiralities means that domain walls are going to move.
No. I mean, chironity is chironity, right? It tells you how it rotates. And here I just tell you that because of the spin-opt coupling, if you try to move this domain wall, then this there would be dynamics in the chironity basis. It would start to rotate the qubit. Yeah. And eventually, if we project out this real space wave function, then we eventually arrive at a very simply looking Hamiltonian. I'll tell you more about this Hamiltonian in the next slide. Okay, so we have this tau x, which simply describes the tunneling rate between these two chironic states. And as you can see, this part may be familiar to you. This is just the standard tunneling rate from the instant calculation that you can find in textbook. And importantly, I want to point out that there's another renormalization factor due to this spin-opt coupling. And we also have this tau z, which is the detuning, describes the energy difference between these two. As I said before, it is proportional to the magnetic field in the x direction. And also, when there's a velocity, it's also proportional to the velocity of the domain wall. And if you plug in numbers, the qubit splitting is typically on the several gigahertz. Of course, we also couldn't just shuttle this domain wall with infinite fast speed because we want to keep everything in the low energy manifold. We don't want to excite higher excited states. That would put us a constraint, and turns out the velocity should be smaller than 100 meters per second, which I think is still pretty fast. Okay, So what I said so far is kind of a semi-classical. We take the whole system. We focus on use this kind of collective coordinates x and phi, and then we quantize them. We project onto low energy manifold. I mean, that kind of makes sense and allow us to do everything analytically. But it would be nice to check the quantum limit. So that's what we did with our friends from Japan. We did this DMRG for this quantum spin 1/2 chain. And you can see the Hamiltonian is, we have all the same ingredients as we have before. Some anisotropies, some magnetic field in x and y directions. And this last term is just the boundary field to impose the boundary condition. We did more studies, but here I just want to show you this energy plot. So this is the ground state. This is the first excited state. And we can see that it's clear when the magnetic field in the x direction is positive, basically it's applied in this x direction. Then this ground state is the positive chiral state, and the first excited state is the negative chiral state. And also, if we flip the direction of the magnetic field, then we also flip the chirality. Of course, this can be also used as a way to initialize the qubits. Another thing I want to point out is, you say the qubit frequency in this case is about like 1 gigahertz, and the energy gap from the first excited state to higher excited state from the simulation is about 10 gigahertz. So it's kind of well isolated from the other higher energy states. And if you fit this kind of a plot with some curves, you will find that we basically get the Hamiltonian I just showed before. Okay, so this is just a story about the simulation. Let's back to the qubits. To implement qubit gates, there are many ways to do it. For example, the simplest way probably is just to move this domain wall with a constant velocity. Then naturally, this Hamiltonian would give us some rotations around some axis, which of course is also tunable, for example, by the magnetic field or by the velocity of the domain wall. And you can also shake this domain wall on the racetrack. In this way, this mathematically is kind of standard story. When the pulse is in phase, then we get a rotation around the x-axis. When the pulse is out of phase, we get a rotation around the y-axis. So for the two qubit gates, then we need, in this simple story, we need two, for example, parallel racetracks. So they can talk to each other through direct dipolar interaction, or you can also put one on top of each other. Then they can talk to each other through this space layer RKKY type of exchange interaction, whatever. And then you do the same story, project onto this chirality basis. You would arrive at this very simple interaction between the qubits. One important feature is that these two domain walls, they can only talk to each other when they can see each other, meaning that this interaction is only sizable when this distance between them, this d, is comparable to the domain wall size. Otherwise, it would decay exponentially. So to realize this kind of two-qubit gate, then we just need to move, for example, the upper domain wall across the another one in this lower panel. For example, if we assume the velocity is a constant, then we essentially realize a C0 gate up to some single qubit rotations. Just give you some numbers. When the interaction strength is around 50 megahertz, and the velocity we need is about 20 meters per second, and the corresponding gate time is in the sub-nanosecond regime, which is pretty fast. And I also want to point out that here is just some simple math, but we also did the DMRG real-time simulation for two quantum spin chain, but I didn't show it here. If you're interested in that, you can check out our archive paper. Okay, so for readout, I think we already have a lot of talks on possible ways to read it out. To read it out, we need some hybrid system, generally speaking. For example, we can use n-way centers to say the chirality, because for different chiralities, it would naturally have different overall spin configuration, and that should give us a different signal in the N-way. And also, you can couple to some other qubit, superconducting qubit, spin qubit, or some bosonic mode like microwave cavity, whatever. That's all possible, depending on what they have in their lab, I guess. Okay, so we also estimate the lifetime, assume the velocity of the domain wall is 20 meters per second, the temperature is 50 millikelvin, and the Gilbert damping is 10 to the negative 5. Then the lifetime is about a sub-microsecond regime, which is kind of decent, I would say. And the quantity factor is about 1,000. Another important quantity is this so-called coherent shortening distance, which is essentially the distance that this domain wall can travel within the lifetime, which is about several micrometers. Okay, so so far what I told you is like how to use this domain wall textures as a typical qubits for quantum computing, in principle. But why we do this? I mean, compared to other existing platforms, I would say that this kind of topological textures, they are solitons, they are naturally mobile, and also, especially considering that there are already a lot of experimental evidence activities in our community controlling this motion of these topological textures. So why not harness and utilize this fact? So to this end, one natural way to use it is to move it and communicate a distant point. And as also Dennis mentioned, it's important to communicate distant point, and it's also important eventually for scaling up. So there are Magnon-based scheme Dennis just mentioned, where Magnon can mediate coherent couplings. And I think it's also an opportunity for me to advertise another line of my research. So the Magnons can also mediate deceptive couplings. That's another opposite regime as this one. In this case, so this figure is from this PRB paper I wrote still with my PhD advisor. So where we look at the regime where the coherent coupling is 0, and we have only deceptive process, and that can also generate some entanglement. And then in this second paper, we look into the effect when the environment is non-Markovian. And we also wrote up a review last year on this kind of deceptive dynamics in magnetic system. So if you are interested in this kind of research, physics, whatever, feel free to check them out also. Okay, so apart from Magnons, we also have topological textures, in our system. So it's natural to think about how to use topological textures to communicate distant points. The kind of hybrid architecture we have in our mind is like you have certain bunch of stationary qubits. They can be spin qubit or domain wall qubit or Skyrmian qubit. Just put your favorite qubit here, and then couple to a racetrack. And hopefully, by moving these textures in the racetrack, we can realize, for example, entangling between distant qubits or state transfer or remote 2-qubit gate. Okay, then I need to hurry up a little bit, but anyway. So then the first thing, of course, is to write down the interaction. Here we just assume it's exchanging coupled. So this sigma is for the stationary qubits, and the tau is again for the domain wall qubits. And this small g is the profile, which of course depends on where the domain wall is. So when the domain wall is right beneath the spin qubit, the entanglement, the coupling is maximal. When we move it away from this position, then it decays exponentially. Okay, so I'll probably just very briefly mention how we do it. Well, if you think about how can we realize this kind of process, it's very simple. That this is the minimum setup. You have like 2 distant spin qubits and let's say assuming they are spin qubits. We actually also checked for skyrmion qubit. It's a little bit different, but I won't talk about that. Maybe in the next talk, I don't know. Anyway, the idea is we hopefully, when we move this domain wall across this spin qubits, they talk to each other through this interaction and get entangled after this process. And then we keep moving this domain wall towards the second one. When it's approaching the second domain wall, spin qubit, they also talk to each other through this same interaction. But in this case, hopefully, they can swap their state such that at the end of the process, these two stationary qubits, they get entangled, while these domain wall textures, they are perfectly disentangled from the setup, from the system. OK, we show it's possible basically by changing the velocity of these domain wall textures. Basically, by changing the velocity of the domain wall, you can change how long they talk to each other. Then you accumulate different phase. When you have different phase, you can get different gates. You can have entangling gate, or you can have swap gate. And also, we estimate various, like time, operational time, the infidelity. So the operational time is typically is in the nanosecond regime, and the infidelity is kind of distant, is 10 to the negative 2. Here are more possibilities. It's really like a train system. You have a station, you have a train system. Hopefully there's no delay anyway. You can use it to realize quantum state transfer or distant 2-qubit gates. We discuss everything in detail in our paper. So anyway, hopefully I convinced you that this kind of topological textures, they are not only good for quantum computing, but also it's good for communicating distant point on solid state form. We don't need other like resonators or whatever. They can do it just by itself. And it's good for scaling up. And yeah, and thank you. And yeah, that's all.